It's bad because we can't check how well we're doing. Yeah, no, because I don't have time.
Oh, you can pay.
No, absolutely, but it's so it complicates things. I'm not saying it might be the word that you can you're right that you can.
I know the person, but I know she was the PI, and I wanted to.
All right, so thank you for the session of this tutorial. Introduce our speaker for the tutorial. I have two announcements. We also have a public talk this evening at 7 p.m. Is that right? At 7 p.m. by Nicole Yunger Halpern. So please all come for that. You are welcome to join for that. That's here in white. It is quantum steampunk. It happens to overlap with the speaker of our tutorial, but it will be a different topic. So please join for that. There will be an informal pizza and drinks reception after all the sessions in Bergen. And just by a show of hands, because I know we were counting on some people maybe making their plans to travel away. By a show of hands, how many are going to be there in the afternoon for food? Almost everybody. Okay, good. So we will make sure that there's enough pizza and drinks. And then, oh, good, yes. Okay, so the final, maybe most important thing that I wanted to do right now is to ask everybody who is wearing the yellow lanyard or has been volunteering for this conference to just stand up for a second. Because really, as you stand up and I say, look at all these great people, students, local committee, maybe you have a local committee, come on, stand up. It's been really a lot of work, and yeah, thank you.
Including for like the play yesterday.
And yes, the song was really amazing. Alright, so with that, I will give it to Karen.
Hi everyone, my name is Jared. Actually, it's pronounced as Jen, but okay.
So today our tutorial is going to be given by Nicole Yunger Halpern. Nicole is a theoretical physicist at NIST and a professor of physics at University of Maryland, and also a fellow of the Joint Center for Quantum Information and Computer Science at the University of Maryland. Nicole completed her PhD at Caltech, studying quantum thermodynamics. Her research is quantum thermodynamics and quantum information theory. And among many other prizes, her PhD thesis was recognized with Ilya Pereguman Prize for thermodynamics. And today, Nicole will be telling us about useful autonomous quantum machines. I'm looking forward to it.
Great, thanks very much. Thanks to the organizers for the invitation to speak here, and thanks to all of you for making it to the last afternoon. So, I'm curious as to whether anyone who has not read anything relevant by me knows what the first automaton was. And to give you a little time to think, by automaton, I mean a machine that performs some task without needing time-dependent external control. A clock. So there are a number of those that do require time-dependent external control. I think it would be interesting to think about what classical autonomous quantum clocks look like. Maybe we could argue there are some in biology. I was maybe a little implicitly here thinking about a human-built machine. At least the one that I could come up with was a pigeon powered by steam. It was built by Archytas of Tarentum, who was a mathematician and engineer in ancient Greece. So that might have been the first. Across history, especially around the 1800s, some engineers did build automata, in large part so that wealthy people could show them off, show how impressive their collections were, and entertain people. For example, Jacques de Vaucanson was a French engineer. He built this duck that appeared to eat grains and then expel them afterward. So this was called the digesting duck or the defecating duck. But a change happened during the 1800s. Automata became useful on large scales. For example, Jacques de Vaucanson also designed a mechanical loom. Mechanical looms helped to usher in the Industrial Revolution, which changed the face of civilization. Nowadays, we have drones that deliver packages and self-driving cars and all sorts of things. Quantum automata have started out on a trajectory that I hope ends up similar. Folks have proposed autonomous quantum engines, refrigerators, and clocks. And again, by autonomous, I mean that these machines don't require time-dependent external control. A lot of this work, not all, but a lot of it has happened within quantum thermodynamics. There are a number of people here who work on quantum thermodynamics, so feel free to refer to a number of your colleagues here if you have further questions. But as a brief overview of quantum thermodynamics, the basic idea is that thermodynamics, the study of energy, was developed during the 1800s for large classical systems like steam engines, but small and quantum systems have heat and energy flows that are relevant to them too. So in quantum thermodynamics, we apply tools from quantum information science to ask in part precisely how do the laws of thermodynamics extend to small and quantum systems, and can we actually prove from quantum mechanics more fine-grained versions of those laws? We also say we know from quantum information science that quantum phenomena like entanglement can enhance information processing tasks. Just as there are information processing tasks, there are thermodynamic tasks like charging batteries and cooling systems. So to what extent can we use quantum phenomena to enhance energy processing tasks? And finally, we look at systems that are processing energy and ask, what can these systems exhibit if they're quantum and not classical? So we use thermodynamics to understand better the division between the quantum and the classical worlds. If you're interested more in this field as a whole, I can suggest these two reviews and textbook. Also, there's this more informal book for the general public about which I'll be giving a talk tonight. A few autonomous quantum machines operate in nature. For instance, we have autonomous quantum switches that transduce energy in our eyes. A small number of autonomous quantum machines have been built in laboratories. I think this work is extremely impressive. It is difficult to do. It's just not really useful. And suppose that we have a single atom quantum engine. I think that's a really remarkable feat. Just, we have to cool the atom, we have to trap it. That takes a lot of work. The atom is very small. It's not going to give us a lot of energy per cycle. And so the engine probably won't earn its keep. So I would like quantum analogs of the mechanical loom, useful autonomous quantum machines. In this talk, in large parts, I'm going to focus on one example that I know of. This is an autonomous quantum refrigerator that, in principle, could service quantum computers by resetting qubits for them. I'll start by explaining the general setup. I'll explain how this autonomous quantum refrigerator works. I'll provide some information about the experiment and assess how well it works. And I'll show some of the details of the thermodynamics arguments for assessing some of these machines. Then I'll step back and ask more broadly, what does it take to build useful autonomous quantum machines? This question was the subject of this forward-looking perspective that co-authors and I published last year. Here's the setting of the autonomous quantum refrigerator. This project was a collaborator with Simone Gasparinetti. He's an experimentalist at Chalmers University in Sweden. He has a superconducting qubit lab, and folks at Chalmers are building a superconducting qubit quantum computer that is externally controlled. As a matter of fact, this is a photo of the first co-author on our paper, Amir Ali. Suppose that we have a quantum computer in this beautiful dilution refrigerator. We have just finished a quantum computation, and we want to perform the next one. We need to reset the qubits. In the context of superconducting qubits, this means that we need to cool the qubits down even more. One might think, but we have this gorgeous dilution refrigerator. Isn't that what it's supposed to do? It doesn't quite succeed. If we allow a qubit to thermalize at the center of this dilution refrigerator as much as it possibly can, it would be at a temperature of about 45 to 70 millikelvin, which granted is pretty cold, but still not quite cold enough in the context of quantum error correction and wanting to avoid errors, because there are non-equilibrium excitations that keep the qubits from getting to the 10 or so millikelvin that is the temperature at the center of this dilution refrigerator. Of course, people have come up with clever strategies for getting around this problem and resetting their qubits. For example, we could measure every qubit's sigma z. If we find that the qubit is not in its ground state, we can flip it. Alternatively, we can connect our qubits to resonators and then drive the qubits in such a way that any excitations they have flow into the resonators, which will then dissipate the energy to the environment. And via this strategy, in very recent experiments, 40 to 49 millikelvin were reached. Those are good techniques. People using superconducting qubits have been doing excellent jobs in resetting their qubits and actually running quantum computations, but we might still hope for maybe some means of advancements. But first, we might want to reduce the external control required. External control is administered by control wires that have to come up to the qubits on the chip that has our superconducting qubits, and we can fit only so many wires on our chip. So the need for classical external control limits the geometries achievable on our chip. Also, control wires are classical. They're relatively hot. They can contribute to decoherence. So we might want to reduce the amount of external control required. Second, we could hope to reach even lower temperatures. So we had an idea. Suppose that we stick a quantum refrigerator inside of this classical refrigerator. This classical refrigerator is already cold because we've been running a quantum computation and we want to run the next one. Therefore, keeping this quantum refrigerator cold doesn't cost us much extra energy. It's not like we're cooling down the whole dilution refrigerator in order to keep our quantum refrigerator cold. Also, this dilution refrigerator has different stages or different layers. And different layers are at different temperatures. The outer layers are warmer than the inner layers. We can give our quantum refrigerator access to one of the outer layers via a waveguide. And since our quantum refrigerator is also at the innermost stage, it has access to a warmer environment and a colder environment. It has access to a temperature gradient. If you say temperature gradient to a thermodynamicist, then they might say, aha, this can be a source of free energy. So essentially, this autonomous quantum refrigerator extracts its own free energy from the temperature gradient and uses it to pump heat out of qubits to reset them. And in the proof-of-principle experiments performed by Ali and the rest of Simona's team, the temperature reached in steady state was about 22 millikelvin, which is relatively good considering the numbers that we just saw. But here's some more detail about how this autonomous quantum refrigerator works. It consists of 3 qubits. Probably most people know this, but just in case, a qubit is a d-level quantum system. For instance, qubits are 2-level quantum systems. We have a hot qubit, a cold qutrit, and the target qubit, which is what we want to reset. I'm going to label the energy levels as 0, 1, and 2. The hot qubit is coupled to a hot bath, and the cold qubit is coupled to a cold bath. In this proof-of-principle experiment, the baths had the form of radiation in waveguides over an appropriate bandwidth. The radiation had a thermal profile. In the most toy model-ish model for this system, we can say, okay, we have superconducting qubits, so we have anharmonic oscillators that have lots and lots of energy levels. Let's truncate the Hamiltonian so that we just have qubits. In particular, we will ignore level 1 of this qutrit because it doesn't really matter. What really matters is the gap here. So in the most toyish model, we have each Hamiltonian proportional to just sigma z. I'm setting Planck's reduced constant to 1. Omega j is the frequency for qubit j, and j can stand for hot, cold, or target. In the worst possible case, the target begins completely excited, so we have to pump out the maximum possible amount of energy. Our goal is to cool this target qubit to as close to its ground state as possible. Here's a less toy model. In some more detail, the bare Hamiltonian has this form. So each of our qubits has an oscillator term, and there's an anharmonicity. So this alpha j is the anharmonicity. And the anharmonicity that really matters is the anharmonicity of this qutrit. Also, we have nearest neighbor couplings. So the hot qubit and cold qubit coupled together at a rate g. The nature of this coupling is an excitation can move back and forth. And also, our cold and target qubits can exchange an excitation at a rate g sub ct. And don't worry, I'll give you values of these parameters later. We want to set our Hamiltonian such that it meets this resonance condition. So the hot qubits gap plus the target qubits gap should equal the large gap of this cold qutrit. Now, a thermodynamicist might kind of see this as a manifestation of exact energy conservation, or the first law of thermodynamics. So any energy that comes out of here and here has to be able to go in here. So suppose that this condition is met. We can perform time-independent perturbation theory, detailed in this paper, to get an effective Hamiltonian. The 2-body interactions effectively merge into a 3-body interaction, which has this form. What does it mean? Well, suppose that our system starts in the state 1, 0, 1. So suppose that the hot qubit starts excited, the cold qubit begins in its ground state, and the target qubit begins excited. That state can transform at a rate A into the state 0, 2, 0. So the hot qubit can spit out its excitation, while the target qubit also spits out its excitation. Those excitations pump the cold qubit to its second excited level. So again, we have nearest neighbor two-body interactions effectively combining together into a three-body interaction, which we can also see as a coherent rotation between these two three-body states. There's a theoretical prediction in the same paper for this amplitude. Of course, it depends on the magnitudes of these couplings, as well as differences between the gaps. Now, suppose that this spitting process has just happened. Well, we don't want for the excitation to oscillate back into the hot and target qubits, so the baths should do their job. Namely, the cold qubits, the cold qubits, should be able to spit out its excitation into the cold bath, as governed by this master equation. So rho of t is the time t state of the entire system. We have a coherent term and this dissipative term. So gamma j is the rate of coupling to bath j. This means that bath j can remove an excitation from the states, and this term ensures that the whole state remains normalized. So the hot qubit gets reset to how it was originally, and the cold qubit is ideally dropped back down to its ground state. Well, in summary, the autonomous quantum refrigerator works like this. Microscopically, it has two-body interactions. Those combine into a coherent three-body interaction. This refrigerator uses the difference between the hot and cold baths in order to pump energy out of this target qubit into the cold qubit, which dissipates the energy to the cold bath. That's essentially what's going on. Now, here's some information about the experiments. Again, as a caveat, I am a theorist, so I'll just do the best I can. As I mentioned, the platform consisted of superconducting qubits, particularly transmons. Here's a picture of the chip that my collaborators printed. Each of the crosses represents a qubit, and the other colored parts represent waveguides, so either the hot or cold baths, or excuse me, either the hot and cold baths or a readout resonator. The red stands for hot, the blue stands for cold, and the green stands for the target. When the autonomous quantum refrigerator was performing particularly well, the parameters had these values. Remember, we have hot qubit, cold qubit, and target qubit. The hot qubit has a gap of about 5.3 gigahertz. What really matters here is this is a reasonably sized gap for a superconducting qubit, maybe usable in a quantum computer. The target qubit had a slightly smaller gap, and the cold qubit's gap was tuned to meet that resonance condition. The hot qubit coupled to its bath at a rate of 70 kilohertz. What really matters about this number? It's a few orders of magnitude smaller than this number. So the dissipative dynamics did not totally dominate and wash out the coherent dynamics. Similarly, the cold qubit coupled to its bath at a rate that's a little smaller than its gap. It's interesting to compare to this A. This A was the rate at which the coherent three-body interaction acted. Why might we want these numbers to be somewhat comparable? Well, we said that this is the rate, basically, at which excitations are spat from the hot and target qubits into the cold qubit. Once that spitting happens, we don't want for the excitations to have time to oscillate back into the hot and target qubits. Instead, we want for the excitations to be dissipated into the cold bath. And so these time scales, probably shouldn't be too different. Then the target qubit interacts with its bath at a rate that we can't control. This hot bath is at a temperature of about 5 Kelvin, which is pretty cold, but for a dilution refrigerator, it's not so cold. The cold bath was at 45 millikelvin, and the dilution refrigerator was at 10 millikelvin, but again, if you let a qubit just sit in the dilution refrigerator and thermalize as much as possible, it wouldn't get to 10 millikelvin, it would get to more like 50 millikelvin. But we say that there's some residual population. After the target qubit has thermalized as much as possible, it would look like it's at 50 millikelvin, so it has still some population in its excited state. I've been talking to you about temperatures, but equivalently, I could be talking to you instead about occupation numbers, because the Bose-Einstein distribution relates occupation number to temperature. So if the hot bath is at about 5 Kelvin, it has, on average in it, about 19 excitations. And similarly, if the cold bath is at 45 millikelvin, then it has, on average, far less than 1 excitation. We're going to see excitation numbers in the next slide, the main result. So I'm going to show you a plot. Along the x-axis is how long the experiment has run for in microseconds. There are 2 different regions down here. One is the short time regime. Tick marks are separated by only 2 microseconds. And the long time regime. Tick marks are separated by 20 microseconds. Along the y-axis, we have the excited state population of our target qubit. Most of that excitation is in the first excited state. In some intermediate times, there's a little bit of population in the second excited state, and that was calculated from a model. But most is in the first excited state. So as we'd expect, the y-axis goes to 1, and note that there's a log scale here. Here are the results. First, I would like for you to focus on this green dashed line. This green dashed line represents the lowest excited state population reached by the targets if there's no quantum refrigerator. Also, notice this blue dashed line. That is the excited state population that the target qubit would have if it reached thermal equilibrium with the coldest bath. These are the standards that we want to beat. We want to see that the target qubit ends up with lower excited state populations. That means the autonomous quantum refrigerator is doing something useful beyond just what passive thermalization could accomplish. Different types of markers represent different numbers of excitations in the hot bath, so different temperatures of the hot bath. We might and the curves represent fits to the experimental data. We might expect that if there are lots of excitations in the hot bath, so the hot bath is really hot, then that temperature gradient would be pretty large, and so the autonomous quantum refrigerator would do a pretty good job. And indeed, these x's move downward very quickly in time, and then they come to be quite low. This gray region here represents the noise floor. The noise, in large part, came about due to voltage fluctuations in the circuitry that was used to perform readout. And yeah, there was a lot of care taken in analyzing the statistics down there. The main takeaway of this plot is that we beat these 2 standard lines. So the excited state population goes below what's achievable with just passive thermalization. So the autonomous quantum refrigerator does its job. Here's some more results with more particular numbers. We can analyze a refrigerator in part by analyzing the time needed for a system to cool. So in the presence of the autonomous quantum refrigerator, the energy relaxation time, basically the T1 time of the target qubit, was 230 nanoseconds. What should we compare that to? In the absence of the autonomous quantum refrigerator, the relaxation time was more like 17 microseconds. We define the reset time as the time needed for the excited state population to reach 0.01, or for the target qubit's temperature to reach a little lower than it would via just passive thermalization with its natural environment. The reset time was 970 nanoseconds. I should say that some of the active reset protocols that I mentioned at the beginning of the talk performed better in terms of reset time. But this autonomous quantum refrigerator performed pretty well in terms of the lowest temperature reached. We defined the steady state as the state reached at 105 microseconds. By this time, if the autonomous quantum refrigerator is absent, the target has reached its residual population, where it's basically going to stay. So the lowest temperature reached was about 22 millikelvin. Very different number. What should we compare this number to? We said without the quantum refrigerator, the lowest temperature reached was at least 45 millikelvin, and the active reset protocol that I mentioned earlier achieved 40 to 49 millikelvin. So the autonomous quantum refrigerator is, I think, performing not too badly. We can also compare with an extremely simple prediction from the theory of autonomous quantum refrigerators. That's 18.6 millikelvin, which is, to me, surprisingly close. So here's the formula. And since this is a tutorial, I will derive the formula for you. The derivation is in this review of essentially autonomous quantum machines, either useful or not useful, by Mark Mitchison. So recall we have a hot qubit, a cold qubit, and a target qubit in our system. He wasn't exactly thinking about that setup. So we are going to introduce a sequence of assumptions to take our system and morph it into the system he was thinking of. First, we're going to treat the qubit as a qubit. Again, we're going to ignore the middle level. What really matters is this gap, which is of this size. Second, we'll suppose that the target qubit couples to its own environment just weakly, so that its temperature is mostly determined by the autonomous quantum refrigerator. I'm going to set Boltzmann's constant to 1, and this is kind of the weirdest assumption. I'm going to suppose that the whole thing acts like just one qubit. Again, that sounds weird, but really the qubits couple together, and what's really important about this assumption is that some levels populations determine other levels populations. So here's that qubit, and we can encode the gaps of our original system into the gaps of this qubit. So this 0 to 2 transition encodes the gap of our cold qubits. This 1 to 2 transition encodes the gap of our hot qubits, and this 0 to 1 transition acts like our target qubit. But here's the derivation. We can use Boltzmann statistics in order to calculate the ratio of this 2 levels population to the 0 levels population. That's, of course, an exponential with a negative sign. There's dependence on the gap and the cold bath's temperature. In the same way, we can calculate the ratio of this 2-level population to the amount of this 1-level population. We have our exponential, our gap, and now the hot bath's temperature. Suppose that we want the ratio of these 2 gaps populations. Well, we can take these fractions and multiply them together. So we substitute in from above. But we also have another expression for this ratio here. Again, we use Boltzmann statistics. So this is the target gap, and this is the steady state temperature. So we equate these 2 expressions for P1 over P0, and we solve for the unknown steady state temperature. So that's how we get this formula that depends on the cold gap, the hot gap, and the associated temperatures. We've analyzed our autonomous quantum refrigerator in terms of reset time and also temperature reached. We can do a more traditionally thermodynamic analysis and analyze the coefficient of performance. The coefficient of performance is to a refrigerator what the efficiency is to an engine. The coefficient of performance, like the efficiency, is your bang for your buck. It's what you want divided by what you have to pay. In this case, what we want and what we pay are heat currents. We want for a heat current to come out of the target qubits, and what we pay, the energy that we consume, is the heat current that goes into, or that is processed by the hot qubit. More precisely, this JH is the steady state current of heat that the hot qubit draws from the hot bath. And in math, since this is an average, we have a trace with the Lindblad operator acting, or that is associated with a hot bath, acting on the steady states, and this Hamiltonian means this quantity has dimensions of energy. So here's the expression for the coefficient of performance. We didn't measure it in the experiment because that would have required a huge change of setup, but it was calculated numerically and also really well matched an extremely simple theory prediction. The coefficient of performance reached, or at least in simulations, by our refrigerator was 0.7, and that approximately equals the coefficient of performance of actually a common air conditioner. So some air conditioners they're not called autonomous, they're called absorption, but they act similarly. They kind of extract their own free energy from a temperature gradient. Fortunately, both these coefficients of performance fail to break a Carnot-type bound that comes from assuming that everything is reversible, so we are not breaking the second law of thermodynamics, fortunately. And again, since this is a tutorial, I will derive the Carnot-type bound for you. I think it's a fun example of the really simple thermodynamic manipulations that can show up in the analysis of these machines. I'm going to take the argument from this paper by some friends at Bristol. And our strategy is to break our autonomous refrigerator into an ordinary engine that's followed by an ordinary refrigerator. So our autonomous engine has a hot bath and a cold bath and a target. And heat flows from hot to cold. Heat also flows from the target to cold. We're going to break this machine up to put an engine here and an ordinary refrigerator here. We're also going to use the fact that the optimal autonomous refrigerator is reversible. So the entropy generated is net zero. In some more detail, what does an engine do? It takes heat from a hot bath. It dissipates some of that heat to a cold bath, but it also outputs work. Now, what does an ordinary refrigerator do? It needs work. So some of this work is going to be used to pump energy from the targets into the cold bath. Those are the components and the quantities. Now let's analyze them using the laws of thermodynamics. According to the first law, each of these component machines has to obey conservation of energy. So this heat coming out equals this heat going in minus this work coming out. Similarly, we can apply the first law to the ordinary refrigerator. So this heat coming out equals the sum of these two energy quantities going in. Now let's apply the second law, as well as the notion that the optimal machines are reversible. The engine, because of the engine, this hot bath loses some entropy, and that amount is going to be completely compensated for by the entropy that is generated in the cold bath because of this heat. And we can plug in for these entropy changes. We have heat over temperature, and we can solve for this primed quantity. We can do the same thing with the ordinary refrigerator. So some entropy is going to be lost by the targets. That's going to be completely compensated for by the entropy generated in the cold bath because of this heat. So we plug in for the entropy changes, and we solve for the primed quantities. Now we're going to take our formulae for the two primed quantities and plug from the second law area into the first law area. So from here to here and from here to here. So all told, when we put everything together, we find this relationship between the two heat quantities that ultimately go into our autonomous refrigerator. The coefficient of performance, we said, is the bang we get for our buck. So we substitute in from above, and we get this formula. So we can briefly sanity check the numerator. This might look familiar from analyses of engines. The cold bath is colder than the hot bath. So this whole thing is not negative. Now the bottom is a little bit trickier. Suppose that our autonomous refrigerator has just started acting. This system might be relatively hot, hotter than this system, in which case this is large, this is small, so this looks negative. That's problematic. We don't want a negative coefficient of performance. That doesn't make sense. The reason why this formula does make sense is we apply it just after the autonomous refrigerator has cooled down the target to just below the temperature of the cold bath. That's when this formula kind of switches on and starts being useful. In this regime, the cold bath is warmer than this, so this difference is positive. And so we have a positive coefficient of performance on the whole. All right, so much for our thermodynamic analysis. I think that it's useful to think in detail about how quantum any given quantum machine is, but I want to be very precise about that here. We use a system that has quantized energy levels, so it's quantum by definition. Also, we said that the coherent rotation between the two three-body states is important. However, I don't know of any entanglement or contextuality or magic here. It is possible that some exists. I am skeptical as to whether that plays a very important role, but I would say, at least for some definition of quantum, this is a useful autonomous quantum machine. We should just be precise about how quantum it is. All right, so much for the autonomous quantum refrigerator. I'd now like to step back and talk a bit more about what it means to build a useful autonomous quantum machine. First, I should specify exactly what I mean by autonomous quantum machine. These are three loaded words. So here are our definitions that we put forth in this perspective here. One can argue about what definitions we should attribute to these words, but we think that these are reasonable, and at least we have to specify some definitions in order to make progress. So by a machine, I mean a physical object. It might consist of multiple components working together, and it harnesses energy to accomplish some mission. By autonomous, I mean that the machine's microscopic Hamiltonian remains constant in time. In other words, there's no time-dependent external control of the degrees of freedom that are really working to accomplish this mission. And a thermodynamicist would say that since the Hamiltonian remains constant, there's no thermodynamic work being performed on the system by any external controller. Why am I saying microscopic Hamiltonian? This is in contrast with an effective Hamiltonian, maybe after a rotating wave approximation or something. Now, quantum is a particularly tricky term to define. Here's what I mean, usefully described by the axioms of quantum theory. A quantum system may have some of the following properties. So it could have discrete spectra, entanglements, quantum uncertainty, disturbance by measurement, contextuality, and more. But it doesn't necessarily have to have any one of those phenomena in any given mission. Why do I say usefully? Ultimately, quantum mechanics describes most things in our universe, but we don't need quantum mechanics to describe us. Well, at least in large part as far as we know. But things like footballs. We don't need quantum mechanics to describe that, so we want to focus on what's usefully described by quantum theory. So by quantum, I don't mean non-classical. To me, non-classical is a higher bar. And by non-classical, I mean a phenomenon that absolutely no classical theory can reproduce And at least according to a certain way of thinking, it means there's no ontological model for people who happen to be familiar with the term that is classical and reproduces the phenomenon. Right. So in this perspective, we were inspired by DiVincenzo's criteria. As probably most people here know, David DiVincenzo put forth in 2000 criteria that a platform needs to meet in order to serve as a useful quantum computer. Similarly, we put forth criteria that we believe a platform needs to meet in order to serve as a useful autonomous quantum machine. These autonomous quantum machines can be of multiple types, and they can be made of multiple platforms. As for circuits, keep an eye on the archive this summer. There's going to be a proposal of how to realize useful autonomous quantum gates in each of 3 platforms. And I'd like to talk a little more about autonomous quantum clocks for 2 reasons. One is we had a wonderful talk yesterday by Junyi about non-autonomous quantum clocks, and I just wanted to draw a contrast. So the quantum clocks that are our best clocks today involve measurements and feedback, so they involve external control. But I'm not talking about those, even though those are fantastic and very useful. I'm talking about autonomous clocks of the sort introduced in this paper. So they can, again, essentially extract their own free energy from their environments. The second reason why I'm going to present a simple model for an autonomous quantum clock is it's basically this autonomous quantum refrigerator that we've already seen working in reverse. Here's the simplest model that I know of. It has a cold qubit and a hot qubit, except this time the relationship between the gaps is reversed. So the hot qubit has the larger gap. Also, there's a ladder. This is the target system. It has this Hamiltonian with all of these levels. There's, again, a coherent 3-body interaction. This time, the 0, 1, 0 state goes to the 1, 0, J state. Here's how that interaction looks. So suppose that the cold qubit begins in its ground state, the hot qubit begins excited, and the ladder begins in its ground state. Under this interaction, the hot qubit will now spit out its excitation, which is going to split up into the cold qubit and the ladder system. So the cold qubit gets bounced upward, and the ladder qubit gets excited. Again, we want to have our system satisfy a resonance condition so that this splitting up of the excitation can happen. Then the baths will reset the qubits, and we repeat this process so that the ladder system moves farther and farther up. Then it gets all the way to the top. It should couple to its environment and emit an excitation. So it ticks, and it falls back down, and the cycle happens again. Now, this model that I've shown here, I showed because it's extremely simple. It doesn't perform extremely well in terms of metrics like accuracy and precision. But in this paper, for example, there is a prescription for building up a more complex clockwork so that one can improve those metrics. Basically, you add a lot more of these energy extraction systems. Again, if anyone would like to address this challenge, I recommend the toolkit of quantum thermodynamics. It does seem like just building the quantum machines being built now that are externally controlled is taking an awful lot of effort and cost. So why bother with autonomous quantum machines, which might be even more complicated? Again, control, external control, classical control is a resource. We might not want to spend so much of it. Control wires can limit geometries achievable. They can introduce decoherence as well. The first generation machines that we build probably won't be so useful, but I think that now is a good time to stretch beyond creating just impressive curios to show off and actually build useful autonomous quantum machines. briefly, I'll go back to the autonomous quantum refrigerator and point out a couple of opportunities. One is to scale it up so that multiple qubits can be cooled simultaneously. And another is actually to apply it in the wild to quantum computations to reset qubits. In summary, we said that classical autonomous machines have progressed from the defecating duck stage to the self-driving car stage. I'd argue that quantum autonomous machines are almost at the defecating duck stage, and we should try to bring them to something more like the self-driving car stage. We illustrated with an autonomous quantum refrigerator that could, in principle, service quantum computers by resetting qubits therein. We saw theoretical models and experimental results and thermodynamic analyses. And I have to say, this autonomous quantum refrigerator was a lot more effective than I expected. I thought that it would maybe cool down the target qubit to just below what's achievable with passive thermalization, but it turned out to be competitive with some state-of-the-art schemes in some ways. And let this talk be a call to arms to build useful autonomous quantum machines. Thanks for your time.
Thank you, Nicole. And let's take the questions.
Thanks very much for the interesting talk. In your derivation of the bound, it looked like TC, TH, and the target temperature were all sort of treated on the same footing. And I wonder if you can just comment on that. It seemed like there was definitely a hot reservoir and a cold reservoir in the setup, but I was less clear about the target reservoir temperature.
Okay. In the derivation of the Carnot bound, or Carnot-like bound, this was basically the temperature of the system of interest that's supposed to be cooled. And this was, let's see, let me go back to that slide. That didn't work very well. Usually I just have to do it in the right order. Thank you. We have our hot system, our cold system, and this is the target system that we want to cool. So we will attribute a temperature to it. And suppose, for the sake of this argument, that it's not out of equilibrium, so we can attribute a temperature to it. If we want, then we can imagine that all of these quantities have d's in front of them and are infinitesimal, so that this is maybe the instantaneous temperature.
Thanks. On your thanks for your talk. I'm wondering if in your instantiation of this refrigerator, if it was really necessary for all three of the modes to, or let's say, if you're getting the target, both of the other two modes had to be qubits, and one of them could have been a resonator.
Basically, let's see. So we basically just used the kind of, at the core of what we did was to use the resonance condition between the gaps. So if we have that resonance condition and we don't have to worry about anything like having a perfect harmonic oscillator, and so if we are trying to use this gap, we might accidentally be exciting that gap too if the gaps equal each other. If we don't have to worry about that, then I think we're okay. After all, the superconducting qubits are nonlinear oscillators, so pretty similar.
Yeah, thanks for the very nice tutorial. So you gave a clear definition of autonomous for the autonomous energy at the end. I presume that also applies to the autonomous refrigerator. But can you take us through the details of the autonomous experiment? What sort of control or probe tones go to the system at what point in time, and what signals come out? How are they? Can you give us some more insight in what the actual experiment looks like and how it relates to its autonomous computation?
Yeah, so there are plots that I didn't show that are in the paper. And for example, there's a there's a figure that gives the pulse sequence that shows that the target qubit was actively excited to its top energy level. So we weren't actually performing a quantum computation and taking one of the computational qubits and saying, okay, this is a kind of dirty qubit, let's reset it. The experimentalists were exciting the target qubit all the way. And readout was performed at the end, but it's really when the cooling process was happening that the experimentalists weren't supposed to be touching the system. That said, again, this is a proof of principle experiment, and so the baths were synthesized radiation, and so that is something else that was put in by hand. The idea is if this were used in the wild, then the synthesized radiation would be replaced with just, say, a waveguide that's connected to an outer stage of the dilution refrigerator and the inside of the dilution refrigerator. And then there were some preliminary experiments to check that the three-body interaction worked as expected, and during that experiment there was more control, but because the purpose of that experiment was just to check the three-body interaction, not to perform the cooling process.
Thank you for a very nice talk. I was wondering how easy is it to turn on and off the fridge? Like if you want to not cool the qubits, do you just turn on?
Okay, I didn't hear entirely well. Was the question, how do you turn off the fridge?
Yeah, for example, if you don't want to cool anymore, if you want to do a new computation.
Yes. So you have some options. You could break the couplings, or you could use, say, the hot bath's temperature as a knob. And there's also, I believe, a plot that shows, there is a plot that shows that you can use the hot bath's temperature as a knob.
Thank you.
Hi. Is it on? No. Okay. Thanks for the nice talk. It's more of a curiosity, actually. The refrigerator scheme made me think of some anti-Stokes, cooling by anti-Stokes scattering in a way. And I wonder if that case would also be considered autonomous, even though you would have to need, you'd have to have, for instance, some pump lasers and stimulating laser, or is that already outside of the autonomous assumptions?
Okay, the question is, can we consider anti-Stokes scattering to be autonomous cooling as well?
Yes.
I don't know what anti-Stokes scattering is, unfortunately. I'm sorry.
Okay, well,
but
it's, yeah, I can say.
Thanks for a nice talk, Nicole. So you talked about coherence was sort of relevant to the autonomous refrigerator. What is the impact of dephasing, and like how sensitive is the scheme to that? And is that relevant even to the experiment?
So the experiment was modeled over many more stages than I showed. I just showed 3 stages of modeling. Ultimately, we ended up with the simplest model that seemed to work, and it was mostly stochastic. So we had our 2-level system, 3-level system, and 2-level system. We can write out all of the 3-body states, then get rid of a lot of the 3-body states because they don't really matter. So we end up with a reduced skeleton energy level diagram, and then we say, let the coupling between these 2 special 3-body states be coherent, let everything else be stochastic. And that was one of the most useful models.
So maybe a related question is there a completely classical model where you just have transition rates and probabilities and no coherences, or is there no way to go to that kind of limit and still get the cooling?
So I'd have to I would have to double check, but my impression was this was the simplest model that worked well.
I have a question. So before, okay, in the hot bath is coupled to the hot qubit is coupled to the hot bath with like 3 orders of magnitude smaller coupling. So then, how do you make sure that the state that you write down is actually thermal there? How do you make sure you have a temperature that you can define for your hot qubit?
The experimentalists tended to measure the temperatures of the environment by measuring the populations of the qubits and fitting those to the Bose-Einstein distribution. And, oh, sorry, yes?
So they assume no coherence, basically, like with hot qubit. The state doesn't have, basically.
Yeah, and it is coupled to this environment, so I wouldn't really expect it to have coherence. And speaking of coherence, about Asha's question, one reason why we might think that the coherence rotation between the two three-body states might kind of make sense to be in the minimal model is we built that three-body interaction out of two-body interactions as prescribed by folks working with Marlin Scully, and they did this whole derivation. They were just focusing on a Hamiltonian system, and they derived an effective Hamiltonian. And so this is a two-photon process that's coherently governed. And so that's, since the derivation holds and seems to describe what's going on here, I would kind of expect that maybe the coherence, or that's why I would expect that the coherence is in the minimal model.
Another question. So the self-driving car is, of course, a fantastic example that we've been dreaming of for decades. What would be your dream kind of autonomous quantum machine?
My dream autonomous quantum machine is a quantum machine that builds and services other quantum machines. You asked for a dream.
So, if I understood correctly, the hot qubit is being driven by a narrowband or incoherent radiation. If you made that radiation coherent with the same average photon number, would the setup have worked just as well as a refrigerator? I know it's not autonomous at that point because it's a periodic drive. I understand, but would it have worked?
Yeah, for that reason, I've not considered it, so I can't tell.
Okay, thank you.
But at least our results were presented in terms of average photon numbers, and they did a lot of the work. It might be a little more difficult to translate into temperatures because you don't have the Bose-Einstein distribution to rely on, but you could probably say something like effective temperature and get around it somehow.
Other questions? All right, then let's thank Nicole again.
Oh, I'd like to add about the dream. A few decades ago, quantum computers sounded just as ridiculous, didn't they?
So I remember if you would say G,
That's a very safe
and so then I'm like,
oh,
yeah, okay, yeah.
So I think that could introduce your completely I hope we can extend it to like generic numbers.
Right.
So do you have like
Yeah. Yeah, well, thanks very
oh, okay.
I don't think we ever managed.
Sorry.
There's like an exact
So I am actually
but now
Oh, great. You're American? Sorry, I know you by name, but I never met you. I think I kept missing it. Like KITP or something.
Yeah, there is a break. I will finish quickly and then we join. So yeah, which session are we going to, you know? Okay, Pasquale, Natalia, yeah. That kind of, I would say.
we did find it's when it reaches
Yes.
It's very similar what happened on but it's a bit different in the sense that
And you know
We found that effect.
it's
he actually wrote a paper talking
And what you see is that
we were asking the same question and then Mark
which is better
so then we got to
It's the same line actually as a level of the silver qubit. You guys are using that background on the graph actually then changes the quality of the control. But that's what now we are done because we are doing so one logic into another one physical.
okay, but for example,
And I wanted to consider
you feel the trajectory of
so only temporary because that's the set. If you allow for spatial we know. We know already. Yes, there is another like class.
how long does that last?
It's something before.
they're actually doing this.
Special correlation. Special correlation but they drop.
in fact it's the opposite. It's surprising if you could subtract one temperature to something like this is quantum system. So what do we measure is
So this is also the type here.
one temperature.
Let's try to say anymore to say that because it's a bombshell. Okay, thank you for no why. We don't macroscopic dynamics.
Radiation coming from radiation from the lines. There is radiation of things that are not quite at the same temperature, right? So it's the yellow flame surrounded by something that might be a little bit